previous video and starting this lecture, we have talked about selection bias as a big problem for causal inference. It's actually the problem that is central in most applications of causal inference techniques. The problem is that units are typically not randomly assigned to treatment, but they are either experimentally assigned an incentive to get treated, or they are not assigned anything. They just choose whatever they want. So people choose to get more education, people choose to go to the gym, firms choose stuff, politicians choose stuff. And what that means for us as researchers is that if we compare the units that have chosen the treatment and those that have not chosen the treatment, there is unobserved differences between those two groups, and that's called selection bias. Then the question comes, well, how can we solve this problem of selection bias? And one step along the way is Heckman's selection model, which was one of the first rigorous and actually ingenious ways of solving the problem of selection bias. Now, this model by now is over 40 years old, and you will no longer see that exact model being applied in top journals these days. But nonetheless, I believe it's important to walk you through the model, because a lot of what came afterwards and what you can see being published in top journals these days actually is based on the Heckman selection model. So let's dive into it. The model is very simple, at least when we take the simplest form of it, which is we just have a regression equation that includes the outcome that we observe, that includes the treatment, and then an unobserved difference in the outcome that is neither explained by the treatment nor by any exogenous variables that determine the outcome. This is the classic thing, the classic issue of unobserved differences. Now, what we do here is we start off here with constant treatment effects, which means that for every person we assume that the treatment effect is the same. And so that obviously simplifies the model dramatically, and then at a later stage in future models that I'll walk you through, we will relax this assumption and allow for heterogeneous treatment effects across people in the population. So here the treatment effects are the same. So for every person, when they get treated, they get the same benefit. However, there is heterogeneity in the model, and the heterogeneity comes from the selection equation itself. So the selection equation is this second equation here, which tells us again that if the gains minus the costs, and the costs is beta z, which is the instrument, plus a random cost parameter that varies across individuals, if that difference is greater than 0, then the person will get the treatment, and if it's less than 0, they will not. Okay? And so again, here we need to apply the revealed preference logic, because D star we don't observe. What we observe is whether they take the treatment or not, and we have to simply assume that if we see that they've taken the treatment, that must mean that for them the gains are greater than the costs. And that the heterogeneity across people here comes from the heterogeneity in costs. The cost of taking the treatment. What we also assume here, and these are the standard assumptions, otherwise we would either the model would not be tractable or we would not have a selection bias, is we assume that these error terms, or these cost, these idiosyncratic cost parameters and idiosyncratic determinants of the outcomes are mean zero. But we have a correlation here between the treatment and this idiosyncratic determinant. Okay, so the treatment is not randomly assigned. There are systematic differences between those people who choose to get treated and those who don't. Now, one way to see this type of model is as a regime switching model, where you have two regimes. So regime one is that the person gets treated. That must mean that the gains from getting treated relative to the cost must be higher, which is implied by this equation here. And so their outcome of those who get treated is that. Okay, so it's the mean outcome, which is mu, plus the determinants that we observe, plus the component that is explained by the treatment, plus whatever their idiosyncratic, individual specific, unobserved determinant of the outcome is. And then the same for regime 2, or let's call it regime 0 rather. Same thing, they did not choose the treatment because supposedly the gains were lower than the costs, and so then their outcome is everything else besides the treatment. But note here that obviously the U could also differ between both groups. And the problem we have here is if we take the expectations, so we want to know what is the difference in outcomes, the difference in outcomes between people who take the treatment and those who do not take the treatment. If we do this conditional on X, or if we just drop X altogether, and we assume that mu is the same across both, we arrive at this. We have the expectation of delta, which is nothing more than delta because it's constant, plus the expectation of U, and I'm just gonna put a dot here because you will see in a second what is behind that dot. Right? And so that again is the selection bias. Now, if we run a regression of the outcome on the X variables and the treatment, the problem is, which is equivalent to what I've just drawn here, the problem is that the model is misspecified. So I get a biased estimate for the treatment effect. Why? Well, because I do not incorporate those expectations. So the expectations that I've drawn, you can't see this behind me here, but the expectations that I've drawn here, the selection bias is nothing more than the difference between, I'm just gonna call them 1 and 2 here, between those two expectations. Okay, so this is the expected unobserved determinant of the outcome of people who've taken the treatment and of those who didn't. And as if the treatment is not randomly assigned, or if you don't have full compliance with the random assignment, then obviously those two expectations differ. And Heckman's great achievement, and also one of the reasons why he was eventually awarded the Nobel Prize in economics, was that he solved this problem with statistics. And when I walk you through this now, it all seems so straightforward and elegant, but getting to that idea to use these techniques to solve that problem was at the time revolutionary. And it shaped how we solve selection bias problems until this day. Okay? Even though the model itself is no longer used very often, this is what it all goes back to. Now, the key ingredient for solving this problem, for basically computing these expectations, is truncated normal distributions. So the idea here is that we make parametric assumptions about the distribution of those unobserved terms in the population, and then we can calculate those expectations based on these assumptions. And the assumption that we're making is that these unobserved determinants, as well as the cost parameter, so the cost of the cost of taking the treatment, that these are all normally distributed, and actually that they're jointly normally distributed. Now let's start with one variable. So suppose U, that unobserved determinant of the outcome, is normally distributed. So let's say we have here, instead of U, I'm using here X because this is what that formula here at the bottom corresponds to. And suppose we have a normal distribution with either mean 0, or here in this case with a mean of mu. So let's call this mu X. And obviously I've drawn this poorly, but the normal distribution would lie between minus infinity and plus infinity. Right? So as the support goes to infinity in either direction, the density goes to 0. Okay? But at anywhere below infinity, plus or minus, the density is positive. So it's a distribution with very long tails and a distribution that is symmetric. Now, what is a truncated normal distribution? What we simply want to have here is we want to have boundaries. So for example, here, let's call this A and let's call this B. And what we want to know is, what is the mean in between A and B? Okay, so what is the mean X between A and B? And the great thing about assuming that it's a normal distribution is that we know from that normal distribution what the mean is. I mean, we obviously have to assume what the mean is, but if we standardize things to mean 0 and standard deviation 1, that's it. So based on the mean and standard deviation and the densities, the probability density function and the cumulative density of those two boundaries, we can actually calculate the mean. And that's a straightforward insight from statistics. It takes a while, if you see this for the first time, to wrap your head around it. But if I know what the shape of the distribution is, then I know exactly let's call this phi A and phi B, what phi A and phi B are, and I also know what the surface under the distribution is for those two points, and then I can calculate the mean of X with that formula. So that's very, very helpful for us. Why? Well, because what we can do in here is the following. Let me quickly erase this. And oops, now the distribution is gone. So let's just draw a new distribution altogether. Chip. Now, again, here we have the mean, but let's say in our case we have a sample selection. So all the people who choose the treatment are those who are rather at the top of that distribution. Okay, so they're not from anywhere in this distribution, but they're more from the top end. Okay, you see people who go to an elite school. If that's the treatment, then they are probably drawn from the the upper tail of the distribution of observed intelligence or of parental wealth or whatever else. And now what we do is, let's say we want to know the mean of x of that variable that underlies that distribution from A upwards. Okay, so we want to know what is the mean of x if x is greater than A. And now obviously we don't have two boundaries, we have just one, but we can use a trick. We can say, well, you know, there is a second boundary that's just plus infinity, right? So B is just at infinity. And if the point is at infinity, then we know that the density is 0. And we also know, if it's at plus infinity, that the cumulative density, as in the surface under the entire distribution, is 1 if we have a standardized distribution. Apologies, in general it's 1. So then when we plug that into the formula here at the bottom, we have mu plus the standard deviation, and then I'm just going to do it down here so you can see it, or sorry, up here so you can see it, plus, and now we just plug in those things that are at this in this fraction. It's the density of A, so that's phi A. That's what we have here, divided by the cumulative density of plus infinity is 1 minus phi A, minus the density that we have up until A. And so the idea is that we want to get the numerator here is the surface of that green part of the distribution. So what we do is we take the entire distribution minus everything up to A, and that gives us the green surface. And so with these parametric assumptions about that variable, we can actually calculate the expectation, or in other words, the mean for different parts of the distribution. And that is exactly what is at the core of Heckman's selection model, and of many models and many approaches that followed here. And what we typically do is then we simply say that we assume that that variable, let's say u, is normally distributed with mean 0 and standard deviation 1. So we standardize it, and then obviously those two terms simply cancel out, and all we're left with is then that fraction here. And so on the next slide, you can see the ingredients with u, and where we standardized u to its standard deviation. And these expectations also have a name. They're called inverse Mills ratios, IMRs. And so the inverse Mills ratio for these unobserved determinants of the outcome, what do they give you? Well, they give you exactly those expectations. They give you the expected unobserved difference between people who have taken the treatment and those who have not taken the treatment. These assumptions in reality may not apply, right? It may be that the error terms are not normally distributed, and then we have to obviously use either a different distribution, or we cannot believe our findings. But in many ways, this is probably not such a bad assumption. And we should at least first check how far this assumption gets us, and then we can always think about more sophisticated, more asymmetric distributions, and so on. Now, if we want to go one step further, and this is what we need for Heckman's selection model. We need to think not only about the truncated distribution of one variable, but we need to think about the truncated normal distribution of two variables at least that are jointly normally distributed. So it's a bit hard to imagine that, but you have to imagine, instead of a bell curve, you just imagine a bell, right? Where you have along 2 dimensions, you then have a bell-shaped density lying over that. Right? And so we have a covariance between those 2 variables. That's sigma uv. And as you can see here, it's actually not a very, it's not very far to go from 1 to 2 variables with these covariances. So what does this mean here? What does that joint normal density, what do we want to measure with that? So go back to our curve with where let's say the variable is u, and we say it's the people who take the treatment are those from the upper tail of that distribution. And now take another distribution for v. We want to know basically what is the mean of v for people whose u is in the upper tail of that distribution. And if they're positively correlated, then probably the people with a high u are also the people with a high v. Or they may be the people that are rather with a low v. They don't need to be exactly in the upper tail of the distribution, but maybe more so than if they were just randomly drawn. That depends on that covariance. Okay, but that's the idea. So we're basically saying among those people whose u is very high, is in that right tail, what is then the average v? What is the average cost of taking the treatment? That's at the core of Heckman's 2-step procedure. What he does then is he says, well, or what he developed was the following. So the idea was, how can we incorporate these inverse Mills ratio that give us the selectivity of people with or units with respect to choosing the treatment or not? How can we incorporate them into a model? So how can we actually take data and estimate that? And the way this works is in a 2-step procedure. So in a first step, what you estimate is the actual selection equation. So the selection equation is a regression here of the observed treatment on the instrument. That cost parameter v, that is individual specific, you don't see. So you only see the actually chosen treatment, and z, the instrument. And if you use x variables, you could also include them. So this is estimated with probit, which gives us then an estimate for alpha and also for beta here. And then we know what the inverse Mills ratio for those two states are. So what is basically the odds ratio? What is the mean unobserved determinant of the outcome among people who've chosen the treatment? We know the formula, that's the inverse Mills ratio. And so we just plug those two things into here. And we also know what the expected unobserved determinant of those who did not take the treatment is. That's the formula down here. And we can also plug in our estimates from the selection equation. Now, one thing that's important here is that we have to also make an identification assumption, because the identification assumption here is that the instrument has affects your apologies. The instrument affects the likelihood of getting treated, but has no direct effect on the outcome. So basically, we have to assume that the correlation between Z and U in the actual equation that determines the outcome is 0. Okay, so it's like with an instrumental variable, that's basically the equivalent to the exclusion restriction. We need to make the exclusion restriction that that instrument only affects the likelihood of getting treated, but not the outcome. Right? This is in some cases relatively straightforward, because typically when we use a Heckman two-step model, we test some choice theory, and we have good theoretical reasons why certain cost shifters or certain shifters of the returns may, for example, affect whether someone takes the treatment, but may not affect then their ultimate choices they're making, because it plausibly does not affect their preferences. So this depends on the context you're studying, and if it's theoretically grounded, that is definitely a plus here. Now, again, back to the two-step procedure. First step is we estimate the parameters that then go into the inverse Mills ratio, and then we plug the inverse Mills ratios here simply into the regression equation. And then we can either simply estimate the first one and the second one and compare the intersets, right? Because here basically, if you think about it as a linear equation, a plus b bx plus delta, then obviously a plus delta is the intercept and b is the slope coefficient. So the way to think about this is that we purge from the outcome, we purge the selectivity. And by comparing those two states then, those who've chosen the treatment and those who did not choose the treatment, while accounting for the fact that those who have chosen the treatment would have had higher outcomes to begin with, we account for that difference. And then the difference we get, our estimate for delta, is free from selection bias. And this is, so because we control here in a non-linear fashion for selection into the treatment, so we have a functional relationship between the actual treatment and the likelihood, or the instrument and the likelihood of getting treated. That is this type of approach also is called a control function approach. And so we include, in an otherwise standard regression model, we include a control function that controls for unobserved selectivity, unobserved selection into treatment. And that's a very important step towards solving the problem of selection bias. Now, we typically these days don't use this approach anymore, but I will show you that even the more modern approaches of marginal treatment effects are very much based on the idea of using parametric assumptions, and in many cases truncated normal distributions, to actually solve the problem of either selection bias or solve the problem of the treatment being way more beneficial for some people than for others. More on that in future videos.